Welcome to my 7th tutoring session in A-level chemistry. In this video, I'll give a detailed explanation about atom, electron, shell, subshell, and atomic orbitals. Atom is the smallest unit of an element. It has a central nucleus that contains positively charged protons and electrically neutral neutrons, with the negatively charged electrons orbiting around the nucleus, the respective shells or energy levels. I have color coded the subatomic particles, yellow referring to the positively charged protons, purple referring to electrically neutral neutrons, and blue referring to negatively charged electrons. In an atom, electrons occupy different energy levels or shells, which are further divided into subshells and orbitals. The electrons occupy different energy levels and sublevels according to the rules governing electronic configuration. In this diagram, you can see the three energy levels with sublevels mentioned only for the first and the second energy levels or shells. Now, where is the electron in an atom, or where do you find the electron in an atom? You find the electron in the shells designated with uppercase letters KLMN, or energy levels mentioned by numbers 1, 2, 3, and these are also called as principal quantum numbers. Within the shells, you find the subshells. The first shell has one subshell, 1s. Second shell has two subshells, 2s and 2p. And the orbitals in the subshells are designated with different letters that are used to indicate different subshells: S, P, D, and F. S orbital is the shape of sphere, and P orbital is dumbbell shaped, or figure 8. Now the p orbitals are oriented along the x, y, and z axis. The electronic configuration of lithium is 1s2, 2s1, or 2, 1, or it is also mentioned with a shorthand notation, with helium being mentioned as a two-letter symbol within the square brackets followed by 2s1. This is because the electronic configuration of helium is 1s2 and is abbreviated as a two-letter symbol mentioned within the square brackets. In the lithium atom, you find two electrons in the first energy level and only one electron in the second energy level. Now, how do you mention this electron present in the second energy level? This can be mentioned using the notation 2s1, where number 2 refers to the shell number or the energy level. Letter S indicates the type of subshell orbital. Here in this case, it is the s orbital. And superscripted number 1 represents the only electron present in the s orbital of the second energy level. The electronic configuration is typically written as a sequence of numbers and letters. The numbers 1, 2 represent the principal quantum number or the shell number, and the letters represent the subshells S, P, D, and F. The superscript numbers denote the number of electrons in each subshell. Each electron shell has a different energy level. Electron shells closest to the nucleus are lower in energy than those farther away. And electrons can move between these shells by either absorbing or releasing energy. This is a different topic altogether, and this will be discussed in detail in my forthcoming tutoring session under the topic flame photometry or flame emission spectroscopy. Aufbau principle states that electrons fill the lowest energy orbitals first before occupying high energy orbitals. It follows the sequence of increasing energy levels and sublevels as defined by the periodic table. Let's consider the electronic configuration of sodium, which has 11 electrons. Electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. So according to the Aufbau principle, the 1s orbital is filled first, followed by the 2s orbital, 2p orbitals, and then the 3s orbital. Therefore, the electronic configuration of sodium is mentioned as 1s2, 2s2, 2p6, 3s1, or 2, 8, 1, or it is also mentioned in the shorthand notation or shorthand representation, where the neon inert gas is mentioned as a two-letter symbol within square brackets, followed by the valence electron 3s1. Now, the importance of electronic configuration is that it provides vital information about the arrangement of electrons in the atom. It could be core electrons or the valence electrons. Now, let me explain the concept of energy levels in the atom, considering sodium as an example. Sodium has atomic number of 11 with 11 protons in its nucleus, and 11 electrons are arranged around the nucleus of sodium atom. 2 electrons in the first shell or energy level, 8 electrons in the second shell or the energy level, and 1 electron in the third energy level or the third shell. Now, the electrons in the first energy level, I am referring to the 1s2. Now, the electrons in the first energy level are very closer to the nucleus, and as a result, they experience a stronger attractive force towards the positively charged protons in the nucleus, and therefore they are at a lower energy level. While the electrons in the third energy level, which is the valence electron in case of sodium atom, they are far away from the nucleus, and therefore they experience a weaker attractive force towards the positively charged protons present in the nucleus. And that is the reason why the electrons present in the third energy level are at a higher energy level. Now let me simplify this representation. So there are 11 protons in the nucleus of sodium atom, 2 electrons in the first shell, 8 electrons in the second shell, and 1 valence electron in the third shell. Now the 2 electrons present in the first shell are very close to the nucleus. Let us consider the distance to be d1. and as a result they experience a stronger attractive force towards the positively charged protons present in the nucleus of sodium atom, while the electrons present in the second shell, they are little far away from the nucleus and experience a lesser attractive force towards the positively charged protons present in the nucleus, while the electrons present in the third shell are far from the nucleus and as a result experience a weaker attractive force towards the positively charged protons present in the nucleus. Therefore, they are at a higher energy level. It is the valence electrons or the electrons present in the outermost shell that participate in the reactions, as it is free from the influence of the positively charged protons. That is they are free from the influence of stronger attractive force exerted by the nucleus of the atom. Now let me explain the arrangement of electrons around the nucleus of atom. Now electrons are distributed or arranged around the nucleus of atom in respective shells or energy levels. You first come across the first shell, also known as the first energy level. That is the K shell. Within the first shell, you find the subshell with 2 electrons present in the s orbital. This is followed by the second shell or energy level, also known as the L shell. Within the second shell, you find the subshell with 2 electrons present in the s orbital, 6 electrons present in the p orbital. This is followed by the third shell or energy level, also known as the M shell. Within the third shell, you find the subshell with 2 electrons present in the s orbital, 6 electrons present in the p orbital, and 10 electrons present in the d orbital. This is followed by the fourth shell or the energy level, also known as the N shell. And within the fourth shell, you find the subshell with 2 electrons present in the s orbital, 6 electrons present in the p orbital, 10 electrons present in the d orbital, and 14 electrons present in the f orbital. Now, the maximum number of electrons that can be accommodated in an orbital is 2. It could be s orbital or p orbital. The maximum number of electrons is 2. While the number of electrons in a shell is equal to 2n square, where n refers to the energy level or the shell number. The first shell can accommodate 2 electrons. When you substitute n with 1, which is the first energy level, you end up with value 2. So 2 electrons are present in the first shell. The second shell has 8 electrons, where n is equal to 2. The third shell has 18 electrons, where n is equal to 3. The fourth shell has 32 electrons, where n is equal to 4. So your number 4 refers to the shell number or the energy level. Now about the orbital notation, the preceding number refers to the shell number. The letter mentions the type of orbital in the subshell. and the superscripted number represents the number of electrons present in that particular orbital. There you go. So here 1s2 refers to the 2 electrons present in the s orbital of first energy level or the first shell. Electrons in an atom are identified by 4 quantum numbers. Principal quantum number determines the energy levels. Azimuthal quantum number describes the shape of orbitals. S orbital is sphere shaped. P orbital is dumbbell shaped or mentioned as figure 8. Magnetic quantum number specifies the orientation of an orbital. For example, the 3p orbitals are oriented along the x, y and z axis, while the spin quantum number describes the spin of an electron in an orbital. So 2 electrons with opposite spins in an s orbital are represented by up and down arrows. So the 2 arrows represent the 2 electrons present in the s orbital. And these electrons present in the s orbital will be of opposite spin. One spinning in the clockwise direction, the other spinning in the anti-clockwise direction. Now the general formula used to calculate the maximum number of electrons in each shell is 2n square. So using this formula, one can calculate the maximum number of electrons that can be accommodated in each shell. Now electrons are arranged or distributed around the nucleus of an atom in their respective shells or energy levels. The first shell, also known as the K shell, has 2 electrons in the s orbital. First shell has one subshell, 1s with 2 electrons. N is equal to 1 for the first shell. Therefore, the maximum number of electrons that can be accommodated in first shell is 2. Moving on to the second shell, also known as the L shell. There's 2 electrons in the s orbital and 6 electrons in the p orbital. Second shell has 2 subshells, 2s and 2p. 2s with 2 electrons and 2p with 6 electrons. So n is equal to 2 for the second shell. And therefore, the maximum number of electrons that can be accommodated in second shell is 8. 2 electrons in the s orbital and 6 electrons in the p orbitals. Now the 2p subshells represent the same energy. That is to say, the p orbitals are of equal energy. Now the electrons present in the orbital can be mentioned or represented with up and down arrows. So each arrow represents one electron, while the oval or the circle represents the orbital. This is followed by the third shell or the third energy level, also known as the M shell. The third shell has 2 electrons in the s orbital, 6 electrons in the p orbital, and 10 electrons in the d orbital. Third shell contains 3 subshells, 3s, 3p and 3d. 3s with 2, 3p with 6 and 3d with 10 electrons. So n is equal to 3 for third shell. Therefore, the maximum number of electrons that can be accommodated in third shell is 18. 2 electrons in the s orbital, 6 electrons in the p orbitals, and 10 electrons in the d orbitals. So again, the 3p subshells represent the same energy. It's also called as the degenerate orbitals, or the orbitals with same energy. This is followed by the fourth shell, or the fourth energy level, also known as the n shell. It has 2 electrons in the s orbital, 6 electrons in the p orbital, 10 electrons in the d orbital, and 14 electrons in the f orbital. Fourth shell contains 4 subshells, 4s, 4p, 4d, and 4f. 4s with 2 electrons, 4p with 6 electrons, 4d with 10 electrons, and 4f with 14 electrons. So a total of 32 electrons. So n is equal to 4 for the fourth shell, and the total number of electrons that can be accommodated in the fourth shell is 32. Now let me explain the energy level diagram in accordance with the Aufbau principle. So the order of energy levels as per the Aufbau principle is s orbital is lesser than p, p is less than d, d is less than f. So the order of filling of orbitals with electrons around the nucleus of an atom based on the order of energy level is as follows. So the filling of orbitals starts with the lowest energy orbital, that is 1s2, followed by 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, and so on. So the order of filling of orbitals with electrons in accordance with the Aufbau principle is purely based on the order of energy levels. First, the orbitals with lower energy are filled first, followed by orbitals with higher energy. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1, or 2, 8, 1, or it is also represented by a shorthand notation with neon, inert gas, represented as a 2-letter symbol mentioned within square brackets followed by 3s1. Now each oval or box represents an orbital. So you can either use the oval notation or the box notation. And each arrow within the oval or box represents an electron. So the spin of electron can be denoted by arrow pointing up or down. So the up and down arrows within the oval or the box, that is the orbital, represents the 2 electrons of opposite spin. So let me end my session with a brief talk about energy levels or shells in halogens. Fluorine has 2 shells or energy levels with electronic configuration 1s2, 2s2, 2p5. Fluorine has 3 shells or energy levels with electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. Bromine has 4 shells or energy levels, while iodine has 5 shells or energy levels. Now the electrons present in the first shell of iodine atom is very close to the nucleus of the iodine atom, with d1 being the distance between the central positively charged nucleus of iodine atom and the first energy level or the first shell. Now the electrons present in the first shell is very close to the nucleus, and therefore the attraction will be greater towards the positively charged protons. An electron will be under the strong influence of the positively charged nucleus, and hence its potential energy and the escaping tendency will be very less. And more energy has to be spent to remove the electrons in the first energy level. Now the electrons present in the fifth energy level is far away from the nucleus. So the attraction will be less. The electron will not be under the strong influence of the positively charged nucleus. Hence its potential energy and escaping tendency will be very high. Less energy has to be spent to remove the electrons in the fifth energy level. So it is the electrons in the outermost shell that participate in chemical reactions. The reason being, the electrons in the outermost shell are far from the nucleus of that particular atom, and it is free from the influence of the positively charged protons. That is the attractive force. So the attractive force will be very less, and therefore the valence electrons of that particular atom will be free to participate in reactions. Thank you so much for watching my video. Hope you enjoyed it, and I'll meet you in my next interesting tutoring session.